Hey folks, welcome back to the series on paper reviews. And sorry, not reviews, but overviews, because these are like 2 minute, 3 minute overviews. So obviously I won't go into details, but still give you an overview. So today I want to talk about like two papers that came out recently. This one, SFT memorizes, RL generalizes, and this one, this has been making a lot of like hype. Um, but it might just be hype. But there's some interesting ideas. But let's see. So in this papers, what the authors claim is when you have a pre-trained model, when you do so, typically the stages of training a model are pre-training, which is just the next word prediction. Then there's SFT phase, which is like an instruction tuning, and then you have reinforcement learning. So here what they say is on top of a pre-trained model, the SFT step, it promotes memorization, while the oral step proposes generalization. And yeah, we'll look into that. But before that, like I'm drinking a very nice beer from Treehouse today. Treehouse is like this famous brewery in Mass, near Springfield, I guess. But yeah, it's amazing. Okay, so right, so this is what they show is, you have your training computation, like, your flops, like how much you're training. And this black line is the out of distribution and then the in distribution. So in distribution, yes, SFT does better, but out of distribution, RL does better. And that's the theme. So they devise a few environments, like, so there's a card game kind of environment where you have to develop like computer 24 using these four cards. I guess you'll have to like find out like whether it's plus, minus, multiplication, division, and so on. And in this environment, the reward the set of rewards they have is you get reward only if it is correct. So the environment gives the reward. There's no like separate reward model. So wrong calculation, you get -1. Illegal number used -5. Correct answer +10. So that's a step. That's a set reward you get from the environment. It's like playing against the environment. So that makes their life easier. There's no reward model that needs to be trained because the environment is a reward generator. And there are two more environments which they play with. And what they find is you take a pre-trained model and you do SFT on a task versus you do RL on a task. For RL, I guess they use PPO, but I'm not. Let me see what RL algorithm they use. Sorry. Yep, they use PPO. Okay. I wonder how would something like what's it called? DPO and all those things will work. But anyway, so the key thing that I want to show you is, let's see. Yeah, so in the different tasks, in the different environments that they test, the in distribution, SFT, which is the black line, the red line, always does better, or somewhat gets closer. But oh, this is a weird one. I don't know what's happening. But when you do out of distribution, you task you train on one task, and then you now have to try it on a completely different task. The RL model generalizes better. The RL training does better. So, which is interesting, right? That's the high level claim that SFT memorizes and RL generalizes. So this makes me think that if you do a bit of SFT, you get this like initial bump in the in domain phase, and then you can do RL. So which is kind of what DeepSeek R1 did. They did a bit of SFT and then did RL. So it kind of like all fits in together. So yeah, so this is an interesting read, this paper. I urge you to check it out in detail. Now, yeah, jumping on to the other one, learning to memorize at test time. This is another direction that people are probing for this long context modeling, right? Like you don't need to like keep all of the context in memory at the same time. What you can do is like, have like a separate module where you only keep the required information and you like, store things that you don't need, pull things that you need. So, this can be called KV cache management, but in KV cache management, you just evict and you forget about it. Here, like you store things, you can like get them, you train them at like, test time. So that's the idea, like having a separate module. And the module is so because of the architecture and everything, they need to do this with linear attention. So they have to they can't do the softmax attention, so they have to do this linear attention to make it more efficient. And the module, the memory module is updated in this fashion. So this is the standard linear attention updates. So the module at time step t, which is a matrix, gets updated with this outer product of like k transpose v for each given step. So this whole thing can be recurrent. And if I want the value, what I can do is like I take the query at the given time step, and I multiply it with this memory module. That's the high level idea, right? We won't go into math. There are some like excellent videos on this, but let me show you the architecture. And then all of this training is done during inference. So when I say training, so this training is for, this is not really training, but it's updating our memory module for each. So whatever input you've given it, updating our memory module for it. And how do you update it? That's given through this, like there's some gradients that are flowing. All right, so we'll skip all the math, and then I'll show you like what actually happens. And this is an interesting plan. So if you have a large sequence, what you do is like you chunk your sequence into smaller bits, smaller chunks, and then you will feed this chunk to the model. So let's say this is my first chunk, or let's say this is my first chunk. So this is my chunk, and now this is not what the model sees. The model will see like a larger version of this. So in this larger version, you first put whatever your chunk is. Then the first few tokens are these, what they call as like persistent memory. So think of them as attention sinks. They're just like learnable parameters. They're like constant parameters that are there. They're like attention sinks. And then you basically use each of these tokens to query with the neural model. And so each token will hit this neural memory. It'll get some response back, basically retrieve another token, and whatever you get is this. So each token you hit, you get something, and then you put whatever you get. So it's like what you've so all the important information that needed to be retrieved for this chunk is retrieved here. And then you put this together and you do an attention over that. And you do the forward pass. And then once you have the attention done, because it's a linear attention, you update your weights. So chunk comes in. So for the first chunk, I guess the memory is empty. Something happens, and then you store whatever you processed back in the neural memory. So when the next chunk comes in, it can retrieve the relevant information. That's the high level idea. So you process your sequence in chunks. And in this experiment, this neural memory is just like a two-layer fully connected network for this. Then they have like different variations of this idea. So this is interesting. This is what attention looks like. So this architecture, what they call is like let's see if I can just or I'll just go here and do this. They call it like this memory as a context. And so if you were just doing chunks at a time, your attention would look like this, right? Like this looks like somewhat like a sliding window attention. This is how your attention would look like. Now, with the now if you were just retrieving things, because for each like whatever sample that you get or each chunk that you get, you retrieve memory in one go. So this is the retrieve, the green, the long-term part, and this is the chunk. So this is what your total attention looks like. And that's how the model, like, so even though these tokens don't seem to attend here, but then their information is contained in these green tokens. That's the whole idea. Then there is so zoom out. Let's go back to the regular phase. So that's the memory as context. Then there's like memory as just gating layer. That's one idea. Like instead of retrieving things, you just have the sequence. You'll put the persistent tokens, and then you'll retrieve tokens, and then these retrieved tokens will act like a gating layer. That's one idea. Then they have memory as a layer in which you just pass the whole thing through the memory, you get what you get, and then you do attention. So, different ideas. And it seems to like do well for a lot of these tasks, actually pretty much state of the art. But yeah, that's the idea behind this paper. But then again, this is not a new idea. There are like a lot of papers, like Learning at Test Time was another paper that did it. And the idea here is that you have a separate module, you process your data in chunks, you store relevant tokens in the separate module, and you retrieve them when you need them. That's the whole idea. And I guess, yeah, so that's it. Like there are like tons of papers I need to like read, but it's a lot of cool stuff is coming out. I saw like a lot of like reasoning stuff is coming out, which is also something I want to pay attention to. But yeah, again, that's all of that is for another video. But right, thanks for watching. See you next time.